Okay, I'm Xifeng from Computer Science Department, UC Santa Barbara. Today I'm going to talk about adaptive inference in pre-trained large language models. This work was done by me, Xuan, and Weizhi. I really hope that my students Xuan and Weizhi can be here and present the work. Unfortunately, they registered the conference, but they're really worried about whether they can go back to the United States. So cancel the registration in last minute. Okay, so I'm sure that everyone is very familiar with Transformer. It has been there for 8 years. But there's one weakness. No matter what the task is, no matter what the tokens are, every token requires the same effort. Copying a sentence takes equivalent computation time as translating that sentence. This certainly doesn't make sense, right? We know that for some tokens, it's much easier to generate. For some hard tokens, you take more computing time to generate. And in this area, there have been a lot of studies. They tried to skip some layers in transformers in order to generate those tokens to save some computing cycles. For example, early exit, speculated decoding, etc. But today, we are thinking about whether we can really do this job in the token level and skip those layers in a dynamic way. Different tokens might bypass different layers. Can we achieve it? Before I'm going to talk about our solution, let me just show you the result. We developed an algorithm called FlexiDepth, which can dynamically skip some layers in transformer. Here I show you 3 tasks. The first task is question answering. The second task is summarization. The third task is a very simple math problem. And we show those generated tokens with different colors. The dark color means you need more layers to generate these tokens. The light color means you don't need all the layers in the transformer to generate the tokens. And you can see clearly, especially from the math example, that for many tokens that has been generated, if you want to regenerate it, you actually don't need all the layers to generate it. So this is the basic idea and the basic result we would like to achieve. And let me introduce our method. Our method is quite simple. Suppose you give me a pre-trained large language model, and we just needed to add a router layer, a very simple neural network, before the attention layer. And this router is going to generate a score between 0 and 1. If this score is greater than a threshold, then we will go through this layer. If this score is below this threshold, we are going to skip this layer. So we freeze all these parameters for the pre-trained language model. We just want to train the router. And if we want to skip this layer, we are going to add an adapt layer here. It's basically quite a simple, small feed-forward neural network. The size is 1/16 of the original feed-forward neural network. Basically, this adapter is going to align the output space with the original output of the feed-forward neural network. And then we also train the adapter, then we are done. And we suspect that this adapter is not needed if the model is fully retrained. But we don't have this GPU power to retrain the full model. And we need to introduce a loss function so that we can encourage to skip some layers. So here we add all of the output of the router, the score together. And this score, sum of the score, represents roughly the number of layers kept during this process. And we use this loss and mix it with the loss of a language model. And the loss can be controlled by a parameter alpha. So basically, you can control how many layers you are going to skip in this transformer architecture. So now we do some experiments. The first experiment is text operation. So we randomly sample 100 paragraphs from the exam test set, and which is a collection of news articles. We do the following 3 tasks. The first one is a copy task. The second one is a summarizing task. The third one is continue writing the paragraph. We roughly know that writing new paragraph is harder than summarization. Summarization is harder than copy the sentence, right? And then we run our algorithm and generate those tokens. And this shows you the average number of layers we need to generate each token. in these tasks. Copy need 22 layers, summarization 28.7 layers, and continuation, the writing, take 30.3 layers. So this roughly aligns with our intuition about the difficulty of those tasks. The second one is math calculation. We randomly generate a set of integers between 10 and 19, and we do the 3 tasks. First one is a copy task. Second one is summation task to sum all these numbers together. And the third one is a multiplication task, multiply these numbers together. And this is the average number of layers needed to generate those tokens per token, okay? 20 layers for copy, 22 layers for addition and multiplication. Still very aligned with our intuition. Multiplication is harder than addition, but the multiplication is easier than writing a new article, new paragraph. And this figure shows you the layer traffic. That means what is the percentage of layers, percentage of tokens go through each layer. So here I show you the layers from 17 to 20 to 32. So we basically use Llama 3 8 billion instruction this model. And you can see clearly that middle layers, actually, we can skip many of the middle layers if the task is not that difficult. So then we compare our method with other existing methods, which although can do some kind of layer skipping with various kinds of constraints. And we show 2 results. The first result is if we just want to skip 4 layers and what the result could be. Amazingly that our method actually can achieve better performance than the vanilla method that doesn't skip any layer. So we suspect that if we can skip some layers dynamically, especially those layers actually does not contribute to the final result, actually the quality, the token quality can be improved, okay? And then we tested to skip 8 layers for these 32 layers Llama 3 model. And we still can achieve similar performance with the vanilla method, showing that there are actually a lot of layers that are not very useful to generate some easy tokens. So we developed the techniques, then we would like to see whether it really can achieve speed up if we put it into the batch mode. And we found that unfortunately, when we skip those layers, they are dynamically. These layers are not, skipping is not synchronized during token generation. Different tokens actually bypass different layers. So if you want to do the token generation in a batch mode, basically it cannot leverage this skipping method to improve the performance. However, this layer skipping shows you that there's underutilized computation in transformer. And recently, we just finished another paper. We will see that maybe we should look at this problem in another angle so that we can take advantage of those underutilized computation. So instead of skipping layers, can we just use these layers to compute future tokens? And if you have read the recent DeepSeek paper, you will see that MTP, they use MTP for the training, multi-token prediction for training. But we think why not just for training, you also can do the inference, right? So here's the idea. When you generate multi-tokens, for the first token, you can go through all the layers. And during this process, you can use some layers to predict the next few tokens. And for the second token and beyond, basically you can go directly to the later layers, for example, the top 8 layers, to generate those tokens without going to the early layers. So we develop an architecture like this called the direct multiple token decoding. Our goal is we want to generate high quality tokens. We do not want to use speculative decoding to verify the token again. And here is the result, very preliminary results. So here MTD2 means we generate 2 tokens consecutively. MTD4 means we generate 4 tokens consecutively. As you can see that even generate 4 tokens consecutively together, you still achieve quite a good performance. It's just 4%, a little bit worse than the vanilla method. And we actually train our model based on Q1, 3, 4B, and we don't have the original training dataset, so we use Tulu V2, 1.5 billion tokens to fine-tune it. But we already achieve such good performance. And we can run this model in a batch size inference framework, it can achieve up to 3 times speed, like performance improvement. And we only use for the second token and subsequent tokens, we only use the last 8 layers of Q1 model to generate those tokens. And we suspect that if we are able to train our model with a larger training set to do the continued training, the performance will further improve. Okay. So for FlexiDepth, we put everything, the code and the model, the data online, and you can visit. And for the new work, this direct multi-token decoding, we are going to release very soon, probably this week on archive, and you can have a look. And we are in the poster 45, and we also are seeking collaboration with additional computer resources and train data, and extend this idea to other architectures, the popular MOE architectures. That's it, and thank you very much.